Okay, so we are now in section 5.5. We are going to be talking about complex eigenvalues. Complex eigenvalues. And we have this 2x2 matrix A. And, well, actually, let me let you copy the example down, okay? Let me let you copy it down, and then we'll go over it. Okay, so complex eigenvalues. We have a matrix A, and we want to find the eigenvalues of A, and then find a basis for each eigenspace located in this. It's not R2, it's C2, which is it's two-dimensional complex space. That's what C2 means. It's two-dimensional complex space, which means the entries of the eigenvectors can be complex values. So complex value, like for instance, if you had 2 plus 3i, that's a complex value. How many remember complex values? It might have been a while, but how many recall complex values in from the past? Sure. Okay. Well, and imaginary numbers, the 3i. So complex value consists of a real part and an imaginary part. But if you just had, and for instance, this here is an element in that. Well, that's just an element in single complex space. But if you had something like say 4, well, 4 is equal to 0, is equal to 4 plus 0 times I. And that's an element in the complex one-dimensional complex space. So complex numbers include real numbers. Okay, they include real numbers. So all right. So how do we find the eigenvalues of the matrix A? Let me see. Matthew says when we factor a polynomial, we will be working with imaginary numbers. Well, I don't know oh, I see what you mean. Yes, you have to consider that eigenvalues could be complex. Yes. You have not had to factor any characteristic polynomial yet. And I think, well, yes, you've had to if for 2x2 matrices. But for 3x3 square matrices and 4x4 square matrices, you've had to find the characteristic polynomial, but you have not had to factor it. But for for 2 by 2 square matrices, you've had to factor those, yes, because you can use quadratic formula. So, okay, we know we need to go after the eigenvalues, so let's do that. Hey, what's this? Finding the eigenvalues. What's this determinant of A minus lambda I equals 0 called? What do we call that? We have a name for that equation. Begins with a C. All right, I have to do a little wheel of fortune. All right, characteristic, good. Characteristic. Hold on, characteristic. Equation, right. It's an equation because we got the equals there. The polynomial is on the left side. That's right, Benny. So, okay, here we go. We've done this before. So determinant, of course, you can use DET, but also the straight bars are notation for a determinant. And okay, so here and here the steps, and then we're gonna multiply things out. So determinant of a 2 by 2, you know how to do the determinant of a 2 by 2. You take the one product and subtract the other product. And then you gather up terms. So hopefully we're good up to here. Okay, are there any questions so far? Okay. Well, can this characteristic equation be factored? Can that be factored? I mean, we want to solve for lambda. We always like to factor. Benjamin, you think you can factor that? I mean, I know they're factors, but offhand, we don't know what the factors are. So, okay, how are we going to solve for lambda? Well, that's okay. I appreciate all participation, Benjamin. It's okay. No problem. No problem. Quadratic formula. No problem, Benjamin. No problem. Okay, so we know how to use the quadratic formula here. All right, and that's what I'm doing right there. Okay, so you know. And we got to just do a little simplifying here. Okay, and hopefully I'll slow down a little bit. I want to make sure everybody's good so far. Okay. That's right, Binyam. We're going to simplify this even more. And we'll go to the next page and look at it simplified. All right. Are we ready to go? Are we ready to go to the next page? All right. So lambda equals 4 plus or minus 6i over 2, which is equal to 4 halves plus or minus 6i over 2, which is equal to 2 plus or minus 3i. So therefore, you have your two eigenvalues. And they are complex. And notice that lambda 1 is 2 plus 3i, lambda 2 is 2 minus 3i. What do we call that? 2 plus 3i, 2 minus 3i. Those are called complex something. There's a word. Complex. There's a name for that. 2 plus 3i, 2 minus 3i. How many remember complex conjugates? Yep, that's what they are. That's what they are. Okay, so when you have a complex eigenvalue, if you're told, for instance, that, hey, one of the complex eigenvalues for this matrix, say, is 2 plus 3i, then there has to be another eigenvalue that's 2 minus 3i. Okay? All right. Now we want to find the eigenvectors. So you know the procedure. You know the procedure. You take, you solve the augmented matrix A minus lambda I, where I is the 2 by 2 identity, then with the zero vector. So we're right here. The conjugates are equal in magnitude and opposite in sign. That's correct, Sega. Okay. Are there any questions on this step here? Maybe give me a few thumbs up if you're good so far. All right. We'll proceed on then. Very good. All right. So now we're here. Now we're here. This is now our augmented matrix. And to find we have to find the eigenvector, and we're finding the eigenvector corresponding to lambda 1 equals 2 plus 3i. So what are we going to have to do? I mean, what do we normally do to find the eigenvector? What do we do with the augmented matrix? We try to get it, okay, Matthew is already saying it. We're trying to get it in reduced form. Okay, and reduced form, echelon form, means that where the negative 2 is, we want a, what do we want there? We want a 0. Okay. So that means I'm going to use the negative 1 minus 3i. That's going to be my pivot. Now I could switch the equations so that the -2 is my pivot, but it actually, I could do that, but let's just do it this way. So I have to multiply -1 minus 3i by a scalar, okay, and a scalar could be a complex scalar, such that when I add the product of the pivot times that scalar, I'll add that product to -2 and get 0. So what I'm going to do first on the right, I note on the right that -1 minus 3i times its conjugate -1 plus 3i. If I FOIL that, first, outer, inner, last, I'm going to get a real number. Because what is I squared equal to? -1, by definition. Imaginary number, imaginary I squared equals -1. And these terms cancel out. Now the reason I'm doing this, well, first, are there any questions here? How many remember that multiplying a complex number by its conjugate gives you a real number? How many recall that? Yeah, I'm sure you've seen that. So now why do I mention that? Because here, the next step, I'm saying, hey, if we multiply the first row by -1 plus 3 over 5 and add the result to the second row and replace the second row with that result, that will get me the 0 where I wanted it. But incidentally, it's also going to get me a 0 in the second spot as well. So the reason is if I multiply -1 minus 3i times -1 plus 3i, which is this part here, that gets me 10. That gets me positive 10. But I don't want positive 10. I want to add a positive 2, because 2 and -2 make 0. So I'm going to take the 10 and divide it by 5. Okay, what I mean is if I take -1 plus 3i and divide it by 5, then when I multiply -1 plus 3i divided by 5 times -1 minus 3i, I'll get a positive 2. And 2 and -2 make 0. But interestingly, 5, well, I mean, it's not hard to see, 5 times like this 5 here times -1 plus 3i over times that 5 times -1 plus 3i over 5 will give you -1 plus 3i, and if you add that to the 1 minus 3i below it, you also get 0. Very interesting. Very interesting. What's this mean? It means the two equations, or the two rows, right? Because the rows are equations. Turns out they're redundant. Okay. So, well, right, and it's like if I always like to think of an analogy here. We know these rows represent equations. So like for instance, just as an aside here, suppose you had, two equations, 2x1. This is now separate. Let's just say you had 2x1 plus 4x2 equals 0. Okay, and then you had 4x1 plus 8x2 equals 0. Again, now this is not related at all to the example we're doing, but I'm trying to relate redundancy to a simpler example. You know, that's all this is just a little example for you to see it. So if you had 2x1 plus 4x, 2 times x1 plus 4 times x2 equals 0, and you had 4 times x1 plus 8 times x2 equals 0, are those equations redundant? They're redundant. So you don't need both equations. You don't need both equations to solve for x1 and x2. I mean, you'll have a free variable, right? But I mean, you don't need the second equation. And it turns out that when you have complex eigenvalues, and you try to find the eigenvector for a complex eigenvalue. We're talking here, you have a 2 by 2. You have to have two equations. The equations are redundant. The second equation is unnecessary. That's correct, Solomon. That's right. And there's a reason for this. There's a reason for this. May I go to the next page and show you why? We're good. All right, we'll go to the next page. So note that this is the system that we're solving. Okay, this is the system that we are solving. This was our original system here. And we're solving it for x1 and x2. But since lambda 1 equals 2 plus 3i was an eigenvalue, okay, it was an eigenvalue, then by definition, the vector x, the eigenvector x, which consists of x1 and x2, that's non-trivial, meaning that the eigenvector x the eigenvector x is not going to equal 0. Okay. Right? The eigenvector, the definition of an eigenvector is it's a non-zero vector. So the vector x is non-trivial. It's not equal to 0. It's not equal to the 0 vector. And that's right, Benjamin. Would it make sense if it did? How would the scaling work? Right. But what this means is, therefore, either of the above equations can be used to express one variable in terms of the other. Okay. So I'll show you something in the whiteboard to sort of, I mean, this whole argument here is it's a nice argument, but it might be a little, maybe a little abstract. I want to make it concrete for you. So I'll continue the problem, but when we're done, I want to go to the whiteboard and give a little more give you a little more intuitive feel for this. So, and then we'll do the rest of the problem. But are we done copying up to here? Who might need a little more time copying up to this blue line here? People are good? Okay, all right, Solon, very good. So don't go any further. Don't go any further than this, blue line right now. Okay, all right. So let me try to give you a feel for this. All right, let me go to the whiteboard. And again, what I'm going to do is I'm going to go back to the little example I had, where I had 2 times x1 plus 4 times x2 equals 0. And then I had 4 times x1 plus 8 times x2 equals 0. Okay, and is the solution vector here is the solution vector non-zero for this redundant equations? So what I'm trying to say, I guess I want to phrase this the right way. Let me just see, one moment here. Well, what is the solution here? What is this? Let me see here. Okay, so x1 equals negative 2x2. And x2 is what? x2 is free. Okay, x2 is free. So yes, I mean, 0, 0, like 0, 0, the zero vector is a solution to every homogeneous system. But the point is, you're allowing for other solutions. You're allowing for other solutions. So I guess maybe a better way to phrase it. A better way to phrase it is that the vector x is equal to negative 2 x2 x2, and that then factors, well, in parametric form, that's x2 times negative 2 and 1. Okay. So that does not, I mean, well, here's the thing. See, in terms of eigenvectors, we're not interested in getting a zero, of eigenvector is 0. But the point is, x2 is free, and you don't let x2 equal to 0, so you can get non-zero eigenvectors. Okay, so it's a let's just say that we're talking that these two equations here were the result of solving, we're finding the basis for an eigenspace, okay? And we get, let me phrase it more carefully here, even better. So I think I can just probably, the basis for the eigenspace is negative 2, 1, right? So in other words, what I'm trying to say is when we have two equations, okay, and they're redundant, we can get a basis for our eigenspace, okay? Now, on the other hand, and so you only need one of the equations to determine the eigenspace. Just like with the complex eigenvalue, the system with the complex eigenvalue, we only needed one of those equations to determine a basis for. We only need to use one of those equations. That's what I'm trying to say. Now, let's say, on the other hand, you have something like this. Let's say you have 2x1 plus 4x2 equals 0. And you have 4x1 plus 4x2 equals 0. Okay, it's a homogeneous system, and these here, are those equations redundant or non-redundant? Good, they are non-redundant equations. Non-redundant. non-redundant equations. Okay, well, what's the, and another way you could look at it is, you could look at it, if you looked at it geometrically, hold on. If you looked at it geometrically, you have an x1, x2 axis. There's a reason I'm doing this. Okay. So the second equation, that's right, Solomon. The second equation is x2 equals negative x1. So equation number 2 here can be written as x2 equals negative x1. And if we draw that, that's what the second equation is going to look like as a graph. X2 equals negative x1. On the other hand, the first equation, 2x1 plus 4x2 equals 0, that would be what? X2 equals, maybe I'll write it down. I'm not be able to do it in my head, right? But 4x2 equals negative 2x1, so x2 equals negative 1/2 x1. So the slope is negative 1/2. Okay, so maybe I'll put that in purple. You have to forgive me if it's not perfect, but it's not bad. This is equation 1, which can be written as x2 equals negative 1/2 x1. And so indeed, the only solution is the origin. So in this case, the vector x, which consists of x1 and x2, is the trivial solution. Okay, it is the trivial solution. So thank you, Christy. So could this system here with non-redundant equations be a system that comes from trying to find an eigenvector? Could this system here with the non-redundant equations be a system of equations that comes from trying to find an eigenbasis for an eigenvalue? Could that happen? Well, can you have an eigenvector x equal to 0, 0? Could an eigenvector x be could it equal the zero vector? By definition, an eigenvector has to be non-trivial, right? So could an eigenvector be equal to the zero vector? No, it can't. It can't. And therefore, the system of equations that yields you the eigenvector, okay, the eigenspace, in this case, you can't have non-redundant equations. The equations have to be redundant so that you can get a solution where the basis vector is non-zero, and hence it's an eigenvector. Okay, does that make sense? Okay, and now I want to tie this in. So this is on the recording, but let me tie this in to what we were just talking about. So again, we are trying to find eigenvectors, okay, for this matrix A. Okay, and we end up, we did the row operation. We didn't have to actually, but I wanted you to just have the experience of doing it. After doing a row operation, we found out that we had a redundant equations. We only need one of them to solve. And again, for the eigenvector. And again, it's because the eigenvector has to be non-trivial. And the only way that's going to happen for a system of two equations and two unknowns is if the equations are redundant. Hence, you can choose which equation you want to use to solve for your eigenvector. You don't have to do any row operations. You just choose one of the two equations and solve for your eigenvector. That's what I'm trying to say. Now, which equation? You got equation 1. Are there any questions on that? All right, the book sort of just makes this a statement, but I want you to have an intuitive feel why it's true. All right, which equation do you want to use? Equation 1 or equation 2 to solve for your eigenvector? Which equation do you want? Do you want equation 1 or equation 2? Which equation looks easier? I agree, equation 2 looks easier. And so that's what I do. That's what I do. I use the second equation because it looks easier. So negative 2x1 plus 1 minus 3ix2 equals 0. And I'm going to solve for x1. And when I do it, I'm going to get x1 equals the scalar, complex scalar, 1 minus 3i over 2 times x2, where x2 is free. Okay? So you don't need to do any row operations. Isn't that nice? For these complex, to find the complex eigenvector? Yeah. Solomon likes it. Noah likes it. Evahar likes it. Sega. And you understand why. Okay, so may I go to the next page? Are we? I want to make sure I'm pacing myself well. Okay, very good, Solomon. Very good, everybody. All right, so Here then is your, you know, the eigenvector x, well, I mean, when you solve for the eigenvector, you get x2 times the complex eigenvector 1 with components 1 minus 3i over 2 and 1. But I want to choose an eigenvector that's simple. So why not just take a multiple, a nice multiple of this eigenvector? If I take a multiple of 2, then I get vector v1. v1 is the eigenvector 1 minus 3i over 2. So any multiple of an eigenvector is an eigenvector. Remember, well, x2 is free, right? x2 is free. So choose x2 to equal 2. You can let x2 be anything, but let it equal 2, and you get a nice, pretty eigenvector. Okay, and so then if you're gonna now you want to go after, well, are there any questions on this? If not, then let's go after the eigenvector for corresponding to the second eigenvalue. Okay. All right. So, okay, well, you know, we set it up. Okay. Yeah, we're going to stay on this page. No problem, Matthew. Same thing. We get here. Okay. And we have to decide which equation, which row do you want to use to solve for your eigenvector. Do you want row 1 or row 2? Okay. Well, people are different. I prefer row 2. But we could also choose row 1, but let's do row 2 here. And maybe we can do row 1 also. But are there any questions before we move to the next page? Okay. Okay. Okay, one moment here. Okay, then let's go to the next page. Thank you. Okay, so here we go, using the second equation. And this part I think is pretty simple. I'll just let you copy it down. Okay, and so then you solve for x, and you get as your basis for your eigenspace, second eigenspace, is going to be the basis eigenvector is going to be 1 plus 3i over 2 and 1. Those are your entries. Okay, and so again, x2 is a free variable, so you can choose x2, let x2 to be equal to 2, and you get a nice pretty eigenvector. Notice that this eigenvector corresponding to the eigenvalue of, hold on here, just make sure I got this right. Yeah, this eigenvector, okay, corresponding to the eigenvalue of 2 minus 3i, is the complex conjugate eigenvector of the eigenvector corresponding to the eigenvalue 2 plus 3i. In other words, the eigenvalues are complex conjugates. The eigenvectors are complex conjugates. Because remember, the first eigenvector was 1 minus 3, the components were 1 minus 3i and 2. I think that's absolutely fascinating. Yeah, so it's like it's like a 2-for-1 sale or something. You know, once you know one eigenvector, you know the other. You don't even have to. I mean, I went through the sort of the step to show you, but it's a method of discovery. I mean, now basically when you find one complex eigenvector, you know what the others can be. You don't have to go through. You find one complex eigenvector, and then you can just state what the other complex eigenvector is. Okay, are there any questions on that? Okay, and I want to show you something in the whiteboard. Are there any may I go to the whiteboard here? Are we good with this so far? All right. I want to address like what if we decided we used the second equation? But what if we decided to use the first equation? Would we get would we get the same eigenspace? The answer is yes, and let me show you. Absolutely. Let me show you. I'll sleep better knowing that that I did this. So the first equation was -1 plus, so the first equation for the system we just looked at was -1 plus 3i times x1 plus 5x2 equals 0. So of course, then x2 will equal, hold on here, one moment. No, what I want to do is I want to solve it for x1. I want to solve this for x1. I could solve it for x2, but x2 was a free variable. So I'm going to solve it for x1. So x1 then would have to equal -5x2 all over -1 plus 3i. We're dividing by a complex number. Right? But what I'm going to do is I'm going to multiply, as Solomon says, conjugate it. I'm going to multiply the top and the bottom by the conjugate of -1 plus 3i. Well, it's not 1 minus 3i. Almost right. The conjugate would be the conjugate of -1 plus 3i. Good, is -1 minus 3i. So then, when we do that, oh, and I mustn't forget, I do have an x2 here, right? The reason I'm doing this is you could see problems where, like, maybe it's a multiple choice and they only give you, one certain answer, and maybe they use the first equation. So, you have to kind of be, you have to be able to work with either equation. So I'm going to distribute the -5 in the numerator, and that's going to give me +5 plus what? Plus 15i, thank you. And then what do we have in the denominator? What's -1 plus 3i times -1 minus 3i? That's going to equal, it's going to equal 10. Absolutely. So then this is going to be then, well, there's a common factor of 5 that goes in 5, 15, and 10. And so that's going to be 1 plus 3i. I mean, maybe, hold on. I always like to kind of do the math, you know. What I'll do is I'll factor 5 out from the numerator. Okay, and then, of course, we got simplification here. Okay, and so what we're going to get is, well, I mean, I don't have to have the x2 on the right there. I can put it in front, right? So we're going to get x2 times 1 plus 3i divided by 2. And that is what x1 equals, right? If you look at the solution we just did, the solution we had x1 as being equal to x2 times 1 plus 3i divided by 2. So you could use either equation, and you got to get the same answer. This one took a little bit of work to see what happens is in the multiple choice. Sometimes in the multiple choice, they'll give you answers in a certain way, and they tend to like the complex number to be, in the numerator. So you might have to do a little bit of manipulation to get to the answer. But at any rate, are we okay on that? Are there any questions on that? Okay, good. Well, on that note, sure, Sega, it's going to take some study, sure. Let me just go into the book here real quick. We have about 5 minutes left, but hold on, that's not where I want to be. Hold on, let me go into the book here. There we go. So let me just get to. Yeah. So they do an example in the book, example 2 here, where they have decimals for the matrix A. And that's okay. You've seen a lot of integers, but decimals are okay. And they go through the process, okay, and they get their eigenvalues for this problem. And they do the same thing that we did. But their eigenvalues are lambda equals 0.8 plus or minus 6i. So that can happen, right? I mean, that's no big deal. And what they do is they end up, they get, they write their eigenvectors as with integer values, which is what you want to do, And MyMathLab probably will want answers with integer values in them. So, like if you type in just some eigenvector that has like decimals, it may not accept the answer. It usually, and it might say use integers for your, your components. So just keep that in mind, There are going to be tremendous advantages to writing your eigenvectors in a nice way. All right, there are going to be tremendous benefits to that. Okay, so I want to stop the recording here for section 5.5. I think we're good.